Okay, so what we are going to do is to talk about sensing, and in particular, little bit of a rehash of what I had done very early in the lectures also, namely sampling of sensors, and then we're going to focus more about processing of sensory information. And so, in essence, we are going to focus on what goes on between the MCU and the various kind of sensors that exist. Some of them analog, some of them digital. And kind of the questions that we are going to seek to answer is how do you acquire data? When do you acquire data? How often do you acquire data? So we saw a little bit of that when we talked about sampling and all. And then how do you process the data? So that's the part which probably won't come today, but on Tuesday we'll sort of get to cover that. So the reason, at some level, if you think about these embedded systems, what they're really doing is they are taking part in kind of you sense the world, then you kind of make some, hope to make some sort of inference about it, like what's the state of the world, and then you are going to act upon it, and that loop kind of goes on and on. And if you look inside this thing of what's the state of the world, there are kind of a few different things which go on. One is we just want to perceive. That's kind of this really what we think about sensing. It's the state of different physical things. And then usually try to make some higher level sense out of it. So it's not sufficient to say, okay, acceleration is this, but you probably want to say, the user is doing cooking. Okay, so some sort of a higher level notion we want to bring out. And then oftentimes it's not simply what's happening right now, but based upon these things, you seek to make some sort of a projection about what will happen later, and then kind of take an action in anticipation of that. So like, for example, is the car going to hit the car in the front? You project that out, and if it seems like the case, then you interject. So I've shown the example of an autonomous vehicle, and whole bunch of sensors there, and they kind of overlap. If you think about it, they're all some tell about location, some tell about what's the state of the car relative to other things around it. So LiDAR, radar, camera, ultrasound, and GPS, these are all kind of different things that come into play. Anyone knows what LiDAR is? Hmm? Well, I mean, so does ultrasound, but yeah. Yeah, so it bounces laser. L is for the, so it's like a radar. Radar shines radio waves, gets it back. Ultrasound is like a sonar, sonic waves, gets the image back. LiDAR and millimeter wave radar, they kind of do the same thing. The difference though is that these are very pencil thin beams. Okay, so they really are not sending out like a radar sends out a signal which just traverses around, kind of bounces back. LiDAR is laser, so it's kind of a very sharp beam which kind of goes out. Millimeter wave is in the same vein. So what all of these things are doing in a way, ultrasound, camera, millimeter wave, and LiDAR, they're taking images. It's just that they're taking images in different parts of the spectrum, and they are taking images either as kind of a one broad brush, kind of a low resolution thing coming out, if you may, or they are taking kind of sharp pencil thin beam, and then you kind of scan it out. Okay, GPS tells you location, GPS tells you speed, acceleration, all kind of moments of the basic position, and it also tells you time, right? GPS can also tell you other things, like for example, actually let me ask you. So let's say I give you a GPS receiver. So location is obvious, that's how it's advertised, and then obviously derivatives of that. Time, less advertised, but GPS gives time also. What else do you think you can use the GPS for? And think kind of more broadly out here, like you have access to the radio signals from the satellites, right? I mean, that's what you have. What else do you think you can infer from it? Well, let's that's a function of distance, function of location, right? I mean, so true, but something perhaps more indirect, more different.
Power places,
Huh?
power places.
How would you do that?
I mean, if GPS is part of any device, you can possibly see how much power that is
I mean, you
using.
can how much
Usage.
GPS is consuming for sure, but GPS in itself will not let you sense anything about the power, right? So some other things you might imagine, depending upon the strength of the GPS signal, you can say, am I inside a building or outside, right? I mean, so radio signals begin to tell you other things also. Okay, what is around me? Is it in that regard? So there are other things you could use GPS for as well. And likewise, a whole bunch of these other sensors, right? I mean, camera is a pretty general purpose sensor. So I guess the thing that I want to bring out is that there are many facets of the state of the world, and these sensors actually capture many of those different things. I mean, we think of camera as just an image, but by appropriately processing it, I can tell a whole bunch of other whole bunch of things that follow from it. So just something to bear in mind, that there's a big gap between kind of the low level sensing and what's the high level thing. So the sensors, if you think about ways in which we kind of use sensors, they're kind of two very broad things. So one is we use sensors for knowledge discovery. What I mean by that is that we use sensors to learn about the world, and then we use what we learn to develop some sort of a model, and then we use that model for kind of like policy making, decision making, and all, right? I mean, the science, if you may, we learn about how the world works. So in that kind of thing is kind of, if you may, the first part, sensor data, and I'm using the term markers and predictors. Kind of the idea is that it's telling me something about the world, some signals about the world. So, for example, how does a disease work? What causes the disease? Something about the environment. All these kind of things you can kind of. So this is knowledge discovery, and a lot of the work that goes on when sensing is used in sciences is along those lines. And typically in these cases, we try to capture raw sensor data, so kind of high frequency raw sensor data, and then scientists, data scientists, analysts, they kind of subject it to all sort of different algorithms to try to look for patterns in it, right? Try to learn a model. So we get to understand what's happening, and then based upon that, then they may develop policies and all. Or alternatively, and that's kind of the other part, we can use this information, and that's a second mode, to intervene, to control the system, to change the state of the physical world. So for example, once we learn what has happened, then maybe we want to keep the person healthy, and by nudging the behavior or by giving medication or things like that. So so that kind of is the final bit, that when sensing gets used to close the loop. So you intervene, you control, you basically affect the change, the state of the world. So very common example nowadays is health type things. We wear sensors and all from this sort of based upon models that scientists have learned through research. Then at kind of runtime, we basically use these models, we take the decision output of them to control things. So that's kind of how sensing gets used. So let's take an example. So this is out of a project from Washington State University, Pullman. And what these guys have been doing is they've been working in this area called aging in place. Essentially, old people sort of at their home, providing assistance for them, looking for their well-being and things like that. And in the process of that, so they have a whole bunch of apartments and houses that they have instrumented, and they try to detect human activity. And the idea is that human activity is useful in two regards. Firstly, if some out of the ordinary thing happen, like fall or whatever, less social interaction, things like that, so that may indicate some problem, and then kind of health caregivers or relatives can be informed. And the other is kind of a more active control, kind of assistive role where if the person is doing something, then perhaps appliances or parts of the home may be in real time adapted in some manner. So when it comes to this application, that the kind of one thing that begins to matter is that what time scale we are looking at here. So they make a distinction between action and activity. So action is kind of like something that's going on a short time scale now. Okay, so like, is the person walking, running? These are examples: chewing, speaking. What's happening on a relatively short time scale, and that's obviously useful and of interest. But there is also a kind of long time scale things, right? I mean, for example, let's say you observe that I opened the faucet in the sink in my kitchen. That's an action, but it could be part of many different activities. It could be I was cleaning up after dinner, or I was in the process of cooking, or maybe I just went there to have a glass of water in the middle of the day. And so that distinguishes between these short time scale things versus what kind of longer time scale, and that kind of these guys term as activity. So in this case, activity might be vacuuming, washing clothes, organizing items, these kind of longer duration things also. So so when we talk about sensing, the thing of interest, the one which we are trying to recognize, may be at many different time scales. Another analogy would be the following: a word and a sentence. Okay, so action is like a word, and the activity is like a complete sentence. So the same word spoken in isolation has some dictionary meaning, but when it's part of a sequence, then that indicates something more. And you can talk about a whole bunch of other kind of things in the process. So sensing gets used in a variety of ways in this manner. So if you look at the typical sensing pipeline, so we have what I guess we normally call as sensors. So on our Hexaware device, these are things like accelerometers and gyros and all. But if you look more broadly, in a typical IoT device, they might be like motion sensors and kind of instruments around you, those kind of things as well. Or it could even be sort of human-generated signals, like microphone on my phone picking up what I'm speaking, things like that. Almost everything starts out analog, or well, everything starts out analog. And then we go through some sort of analog circuitry, amplify, filter, whatnot, and then after that there is kind of this phase which we call as A to D conversion, where we sample the signal and we digitize the signal. And then there is a digital part where we filter the signal, kind of clean it up and all, and then we make some inferences out of it. And inferences are what I was referring to earlier, actions and activities. And then there's probably a spectrum of it, because my interest is in things happening over some relevant kind of time scale. So it could be, what object was it? Who was it? Was it a person? Was it John? The recognizing gesture, I know some of the projects are seeking to do that. What's the activity? What's the location, speed, all sort of things that you can imagine that we try to infer. And as I articulated earlier, oftentimes even that is not sufficient, and then we need to make a projection about it, that this person is going to become stressed, and so let's intervene right now. So you want to take the state thus far and then kind of make some projection about the future. So that's a typical sensing pipeline, and it's pretty varied, as you can imagine. So I'm going to focus kind of this module on the two things: sampling. So we touched upon it a little bit last time, earlier in the course, when I talked about like the sampling rate and stuff like that. So, but we'll go deeper into it, because there's a lot you can do at the sampling state itself. And then we are going to talk about inference. And inference basically means that how do I go around deriving those higher level sort of concepts out of it, actions and activities, or other terms which are used, complex events. Like, for example, let's say it's a hospital and we are trying to monitor that nurses wash their hands before they go from one patient to another patient. So now if you think about it, it's really a stitching of various atomic things. The nurse saw one patient, left the room, entered another room, never went to the sink, never used any sanitizer, went to the other room, and is going, right? So that would be a sequence of things, right? None of them in isolation are indicative of that complex event. So the complex event is kind of a term used, which is taking these things which are separated in time and looking for a pattern in them. So looking for a sentence from kind of a bunch of words that are occurring. So let's do these two things. I'm going to focus on sampling mostly because on the short notice that I had today, I couldn't finish the slides for inferencing. So sort of go with sampling first. And there's a fair bit of interesting work that has happened in that space in recent years, and it's been a topic of a lot of new developments. Actually, and in particular, interestingly, UCLA has had a big role in their math department. Work. So you'll see some of that. Okay, so need for sampling, well, kind of obvious, which is we have to take that analog information and somehow we need to digitize it. So the question that comes up is the following: that how do we go around doing it? So while it is possible in theory for you to capture and store continuous signals as an analog signal, but most of the time it doesn't make much sense, and we are far beyond analog processing in most cases. So so continuous time signals are not very attractive. So what sampling really does is it gives you kind of a current snapshot of a continuous signal, and after we have taken a snapshot, usually there are two things happening there. One is we are sampling in time, and the other is, since we are going into the digital domain, we can't really express the signal as a continuous value also. So we also have to decide how many bits. So there is a discretization which is happening in two regards. There is a discretization in time and there is a discretization of value, both of which kind of take place during this act of sampling. And traditionally, kind of the signal processing part of EE is the one which has dealt with this thing, but actually in recent years, a lot of work has been happening in computer science side, largely because of the way machine learning type systems have begun to play a role out there. But starting from kind of the more basics, so this is something we discussed previously. There is the well-known from close to 100 years ago, the Shannon-Nyquist sampling theorem. So what it sought to answer is the following: that if I am sampling a signal, and for now just discretizing in time, so let's imagine I can capture the signal value in its full resolution, so kind of a real number value, okay? Then intuitively it would seem that if I capture 2 points, what's happening to the information in the middle? Because if I just give you 2 points in the signal, then I can, not knowing anything else, I can draw any arbitrary curve in between, right? So it would appear on the face of it that anytime I'm discretizing or sampling in time, I'm going to irretrievably lose information. So I have to make some additional assumption, right? So in the absence of any assumption about the signal, just taking a few samples, I can draw infinitely many different curves through it. So so that's the act of sampling, and we can, as you can see, we can draw many different curves. So what Shannon-Nyquist theorem says is that if I place one constraint on the signal, namely I know its bandwidth, what's the peak frequency content that it has, then surprisingly I can make a statement about being able to reconstruct the signal perfectly. Okay, so what we are bringing to bear out here is some additional constraint, because in the absence of that, I have infinitely many curves. So if the signal bandwidth is limited, that is, it has a max frequency, and there is no, if I were to take the Fourier transform of the signal, there would be no frequency content beyond that f max, then what this says is that if I were to sample at twice that f max, then I can reconstruct the signal back perfectly. Okay, that there exists a interpolation mechanism which can give the original waveform back, which, or another way of saying is, you can ask me the question, what was the value at time t, and the time t is somewhere in between these sampling points, I would be able to tell you accurately. So but we have to place this restriction, because otherwise there are infinitely many curves. So if the signal is not band limited, that is occupies arbitrary amount of spectrum, then we really cannot recover this thing. So there are two things going on in this thing. So one is, we are making an assumption about the signal. Okay, the assumption is basically that it's band limited. And the second thing that we are doing is, we are saying our goal is to reconstruct the signal. That is, I'm given a waveform, and what I want is a complete waveform out. That latter goal is also often not is not necessarily. Maybe you're only interested in knowing what's the peak of the signal. Maybe you're only interested in knowing what was the average value of the signal. So if I want to know some function of the signal, then obviously this is sufficient but not necessary. You could get away with a lot less in that case. If I were to only ask for a peak, then maybe I don't need all of this thing. Maybe I can do a peak detection in a different manner. So one has to kind of see what this is doing. And the final bit I would say is that all of this holds true if after sampling I'm getting the values of the signal with infinite precision, right? Because if I were to lose that precision, then I'm adding noise to the signal. Okay, so then again I cannot recover things perfectly. But despite all of this, this has been kind of the workhorse of so much stuff we see around us. I mean, in fact, almost all computing, communication, and all deep down is somewhere making use of this fact. We also touched upon this thing earlier, that if, let's say, perchance you are wrong about what the maximum frequency is, and you were to sample it at less than twice the maximum frequency, then what happens is that the act of sampling in time can be viewed as repeating the spectrum with the sampling frequency. And so if the sampling frequency is not high enough, then these replicas begin to collide, and essentially your signal gets distorted. So you can never recover it. And to make sure that this doesn't happen, usually what is done is that in front of the A to D converter, there would be an analog filter which will make sure that the signal content is kept within bounds. So what therefore the pipeline then looks like is, as shown in this diagram, that very first thing that the signal goes through is some sort of a filter, analog filter, and an anti-aliasing filter. And then we go through this sample and hold, where we basically take a measurement of the signal and put by charging up a capacitor conceptually. And then we quantize it, so we convert it into one of few levels, and then we encode it. So that's what A to D conversion happens. And output of this thing is some digital bits. Usually the A to D converters are designed so that the whole range of the signal is sampled uniformly and the digital bits out are uniform. In some cases though, the output encoding is not uniform. So what I mean by that is, I may say that, most of the time the signal is close to 0. Let me sample finally there, and it reaches the peak less often. So essentially in that case, instead of uniform levels, I may have more crowding in some part and far apart in other parts. This is often done with things like speech or sound, because we want to capture sort of with higher resolution kind of the lower levels, and the peaks perhaps you can get away with coarser sampling. So the telephone system, for example, the sampling they use is kind of non-uniform, and that's a trick one can often use that you spend your bits in that part of the signal which are more important. So that's what kind of goes on out here. The sample and hold, that's the first stage out here. All that happens out here is the following, that there is kind of like a switch which basically turns on, uh, connects the analog signal to the capacitor, so that voltage out here charges at the capacitor. So we turn the switch on for a little bit of time, and then we open it and we connect it to the discrete signal, and then we digitize this part. So we collect charge for some duration delta t. That gives us a charge proportional to the voltage on the analog side, and then we take this charge and then do a level comparison. So the reason we are doing it, so that while we are digitizing, we are not chasing a changing signal. So we take a snapshot, collect a charge proportional to the voltage at that time, and now we have some time to actually do the digitization work, and then we kind of repeat this process. So that's the sampling part, and then the digitization, or kind of the quantization, is essentially a process of comparison, right? You are going to take the charge on the capacitor, and conceptually you have to compare it with a whole bunch of thresholds to decide which bin it lies in. So the thresholds I'm referring to are these different threshold voltages. So we'll basically compare it against each one of these conceptually, and then say, aha, it lies in this bin, and therefore the code is 101. Now, to do that comparison, much like you would do comparison in real life, you can either do it sequentially, so check it one by one again, or you can do it in parallel, or some other ways of doing that comparison. So the quantization phase is basically a process of finding the right bin, and it's really a problem of comparing against a bunch of thresholds. So what matters for us out here is the number of bits, because the more bits you have, the finer the bins, and therefore more accurately can you represent the analog signal. Hexaware and usually MCUs in this range tend to have maybe 8 to 12 bits kind of quantization. For certain applications where you need to measure very fine things, maybe you'll go to 16 bits or perhaps even 20 bits. Seismologists and all, these are the people who try to look for very weak signals, and so they may have more things. Another thing that happens is there is some pretty advanced, more advanced concepts which also show that if you sample faster, even faster than what the 2 times f max would say, then you can get away with fewer bits. So there is a trade-off between sampling rate and bits. So I can reduce the number of bits and I can sample faster. So I could, and for example, even though my signal maybe, let's say, require only a sampling rate of 2 kilohertz, but I can sample it at, let's say, 10 kilohertz and then trade it off against lower bits. So those are the kind of things that people who design A to D converters and all try to exploit, that this kind of a trade-off that one has to do. Another thing I would say is that we are talking about here in time, but it's the same thing about space also. So let's say I want to reconstruct the light field on the floor of this room, and I'm going to put light sensors at various places. So now you can think of the problem as one of how far apart should I place the light sensors so that I can reconstruct. So if you look at the lighting on the floor, there are regions of shadow and brightness, and they have some variation. So there is a spatial frequency, and the same concepts of Nyquist rate and all now apply in 2 dimension. So you might, as you might imagine, that if the frequency content of the light field in the room was relatively smooth, that is low frequency, then I don't have to sample that highly. On the other hand, something like this, where there are lots of regions of shadows and all, the frequency content is high, so perhaps I would need a denser deployment of sensors. So it's the same concept carries over in these other dimensions also. It can also apply to, let's say there was a robot and it was going around sampling in space. Maybe it's sampling for pollution, or maybe it's sampling for I don't know, radiation level or stuff like that. Same concept applies. If we know something about the um, the spatial frequency, I can use that to drive the robot to say something about that's going on. So quantization, encoding, and sample and hold. And that comparison part, as I said, there are many different ways of orchestrating it. I can do a parallel comparison. So all this is happening in this thing called parallel or flash A to D. What I do is we create a bunch of thresholds using a series of resistors. So we take our voltage, we divide it into a bunch of equal bits, and then the actual signal V in, we compare against each other. These things are comparators. So essentially, what will happen in this case is that the output of some comparators would be 0, and the ones after that would be 1, and then we use all of that to encode with some simple digital circuit to get our actual coding. So a bunch of comparators, a bunch of a reference voltage with some high quality resistors so that we have thresholds. So for example, if I have a 4-bit A to D converter, then I have 16 thresholds, so I would have 16 resistors, and dividing my voltage into 16 equal levels, and I want to compare against each one of these. Now, as you might imagine, if you were to be asked to give in a variable x, what value is it? This is kind of it's a fast way of doing it. It's very parallel, but it's very expensive because I have an exponential number of things. So,
On the previous slide, you
sure.
had 8 bits of quantizer, right?
Mm-hmm.
How can it then do between 1 over 3 to the 9 and 1 over 3 to the 9?
Yeah, I messed up obviously. It should be a 10-bit quantizer.
Okay.
Yeah. You are watchful. Okay. Okay. So we could, so parallel comparison is the best we could do, but it's obviously slow. So then the other alternative is kind of we do some sort of a sequential thing. We identify, is it in the first bottom half, top half, then we go within that half. We kind of do a recursive thing. So we get 1 bit every time, much like you might do when comparing a number with a program. So these are called successive approximation A to D's converters, but that's basically all they are doing. That there would be some little controller which is going to guide the process so that I'm going to compare the signal against a sequence of thresholds until I find its right bit. And to be able to do this, I need to now supply this guy on a bunch of different thresholds. So we generate a bunch of different thresholds by using a D2A converter. So I take I feed this DAC a digital number, and it's going to generate the corresponding voltage, and I'm going to compare it against that. So we put a DAC in a feedback loop, and then apply this. This, as you imagine, can be a lot cheaper, and therefore a lot of the implementations are kind of done in this particular manner. And you could do it cheaply. The only disadvantage is that since I'm now spending multiple iterations, I'm estimating bit at a time. So this is kind of like n times slower, right? Because if I have to do n approximations in there. No question.
So there's a trade-off between conversion time and resolution. This one obviously takes more time. But why would the resolution of this one be any better or worse?
So now the technology constraints are going to come into play, right? So area cost here is a lot higher, so you may simply just not be able to afford it. So I think to properly formulate the problem, it would be given a cost constraint, which one would achieve something, okay? And that's kind of a bit of a moving target, and in the sense that in some technologies, it could be one way or the other. I mean, you can certainly imagine that doing these resistors on a PC board is going to be insane, right? I mean, if you're looking at 10-bit converter like this, that means you have 1024 resistors and a whole bunch of wiring traces and all, and you have to worry about, are these resistors of equal value because they also have variations among them. So all those issues are going to come into play. This thing has its own set of issues, namely it takes more time. And there are a whole bunch of other A to D architectures also. I mean, there's a reason A to D architect, I mean, there are people who, there are colleagues of mine who have devoted their entire careers to doing nothing but A to D converters because it's an important piece, and making it efficient and fast and higher resolution can pay off in a variety of different ways. So this goes to this issue that sampling could be in any dimension, time or space. So even though usually we think only in terms of time, the space part is also there. So there are some subtle differences though. In time, we can't go back, right? I mean, in the sense that the signal is progressing and we can't say, hey, stop, let me sample, I'll come back again. In case of space, we do have that luxury. That is, if I'm sampling the light field out here, maybe if I take a step which is a bit too much, I can kind of go back and refine my estimate. So causality comes into play, and the fact that time continuously moves and moves in one direction only complicates things. On the other hand, time is one-dimensional, space is two or three-dimensional, so that presents its kind of own challenges. But in spatial sampling, you do have the possibility of going back and refining your estimates. So that is something that you don't have in time. Another set of things, terminology that is often useful to have is upsampling, downsampling, and decimation. So what happens is the following, that upsampling refers to that I want to give you that I have a signal which was sampled at one particular rate, and now I want to give you the signal as if it was sampled at a higher rate. Now that should always be possible, because if I was successfully able to sample a signal at a lower rate, then of course I can certainly sample it at a higher rate. And conceptually, what I can do is I can take that lower rate sample signal, convert it back to the true signal, and then recover and resample it at a higher rate, right? Because I had the lower sample version, I reconstruct it, and I resample it. Of course, that would mean going out into the analog world, coming back. You don't want to do it. So you can do it entirely in the digital side, and that is what the upsampling algorithms do. It is really the problems that come into play is, let's say I give you a signal sample at 1 kilohertz, and I say give me the signal at 2 kilohertz. So you could say, hey, maybe I need to create a sample in between each one of these. Could I just take the average? But that's not necessarily obvious. That why should you take the average? Maybe you know something about the way the signal was changing there. So these algorithms try to be smarter about this process. Then the other challenge is, what if the ratio between the new rate and the old rate was not something obvious like factor of 2? What if it was, I want the new signal to be at 4/3 of the rate of the old signal? Then how do I go around doing it? So these upsampling algorithms kind of do that. A question for you, why do you think, when would this notion be useful? Why would I want to sample at a higher rate? Or why would I want to have a signal sample at a higher rate?
I have kind of a question. So are you interpolating between like two data points basically?
Not quite. I'm regenerating, because remember, I am possibly interpolating, but it's not the standard interpolation algorithms, right? So because you can't simply say, hey, I'm going to average it, or I'm going to average k points on either side, because you really have to look at the overall signal content to be able to do it. So these algorithms kind of do more. My question though is that, could you think of scenarios where you simply, the higher rate sample signal is not actually giving me any new information, right? And even before, I had the entire knowledge of the analog signal. So why do we even bother doing it? Yeah, so it's usually just an interoperability issue. That is, I have to send someone a signal and only accepts some standard data rate signal, right? So maybe my algorithm was trained on accelerometer readings which were at 1 kilohertz, and my sensor is giving me readings at half a kilohertz. So I need to kind of just do that match. So that's what the role of upsampling. Downsampling is trickier. So downsampling, we are saying I have a signal which is sampled as at 1 kilohertz, and I now want to do it at a half a kilohertz. So one has to be careful because you can't always do it. If my original signal had frequency content of half a kilohertz and therefore I had sample at 1 kilohertz sampling rate, then I can't reduce the sampling rate. If I were to reduce it, I will create some aliasing effects. So one has to be careful out here that when we are doing this, when we are reducing the sample rate, I have to also remove the signal content which was above half the new sampling rate. So what this process does is, again, mathematically, it will first remove the part of the signal which is more than half the new sampling rate, and then give you the new version. It can't simply say, let's say I were to say go from 1 kilohertz to half a kilohertz. You can't simply say, let me throw away every alternate sample, because that may create an aliasing effect. Okay, so one has to be careful out here when you are reducing the sampling rate. If you look at the systems more general, like if you look at like Android smartphones, right? Your phones have a whole bunch of sensors. Unfortunately, in these platforms, you really don't have a luxury of specifying any sampling rate. So the way Android sensor API works is, you can basically say, I want a fast sampling rate, or a medium sampling rate, or a slow sampling rate, or something like that. There are kind of a bunch of categories. And then what actual sampling rate you get is at the mercy of the handset provider. There's no real guarantee. So if you're working with, let's say, accelerometer or stuff like that, the high sampling rate on a Samsung phone may mean one thing, and on a Google phone may mean something entirely different, or it may even differ from sensor one model within that manufacturer to another model. And so if you are training an algorithm, it either has to adapt to the sampling rate, or you are going to be stuck running it on a particular type of a model. So one has to kind of be careful about this issue a little bit. And then decimation. So decimation is a process where we actually apply the anti-aliasing filter. We kind of remove the content which was higher than half the new frequency, half the new sample rate. Whereas downsampling refers to when we don't bother doing it. So in case of downsampling, there's a possibility of corruption that is happening. But downsampling is a lot easier because I can just discard samples, whereas decimation requires doing some signal processing, and again, on the other side, but okay, it's tricky to do. So upsampling, downsampling, decimation. In embedded systems specifically, the challenge that comes is that since these things are energy constrained, so an A to D conversion can be significantly power hungry, so one has to be a little bit smart about it, so, or considerably smart about it. So firstly, while it may sound that, oh, I'm just going from 8 bits to 16 bits, but that's a very costly proposition, and you can easily look at, just if you check what's the power consumption of A to D converters, you'll see that these bits come at a significantly higher cost. And you can see why, because in the successive approximation, it's an order n thing, right? So, and if you have any sort of parallelism, there's an exponential component to it. So the power consumption and cost can go up very rapidly. Moreover, every additional bit that you sample and every additional sample that you collect also means you have to process it, and it also means you have to perhaps transmit it somewhere. So redundant sampling, redundant bits, they all add up to extra work. So one also has to be smart about how you go about sampling things. So this goes back to the thing that I said about the Shannon sampling theorem earlier, which is it is a sufficient system. What it does is it tells you that how should I sample so that I can recover the original signal in its entirety. But it's not a necessary condition. It doesn't mean that I have to sample at that rate, because maybe I know something more about this. Remember, so there were two things going on there. One was that only assumption I was making was that the signal was band limited to a certain frequency. Maybe I know more about the signal. Maybe I know that, you know, it's a sine wave. It's just that, or maybe something else, right? And the other thing is, maybe I don't need to reconstruct. Maybe I only am interested in the peak value, or maybe I'm only interested in the median value, or something like that. I don't care about reconstructing. So what we'll seek to answer on Tuesday is, could we be smarter about this sampling? But before I end, let me ask you the following. If I tell you that the signal is a sine wave, how many samples do you need? Any thoughts? How many free parameters does a sine wave have? Amplitude, frequency, and phase. 3. So in theory, 3 samples should suffice, right? Whereas Nyquist says infinite number of samples at more than 2f. Okay, so so that's what we are going